This is a data race. Usually in C++ you spot these miles away. You forgot a mutex or you access the exact same global variable from two different threads. Rookie mistakes. But what if I told you that this code, which accesses completely different indices in completely different memory addresses, is creating a silent race condition that is corrupting our game state? This isn't just a container, it's the single biggest trap in the C++ standard library. Today I'm going to show you why std vector of bool is dangerous and how trying to save memory blew up in my face. To understand the trap, you have to understand the goal. In modern game dev, we usually write gameplay code using object-oriented programming. Actors, classes, virtual functions, that works fine for the player logic. And here is where data-oriented design kicks in. For a mass simulation, like a horde of 100,000 zombies, OOP fails us. Why? Because of the CPU cache line. Here is the hardware reality. Your CPU doesn't fetch variables one by one. It fetches chunks of memory called cache lines, usually 64 bytes at a time. Think of a cache line like a shipping container. In OOP, you order a container just to get one boolean flag. The other 63 bytes are filled with junk padding or other data you don't need right now. You are clogging your memory bandwidth with styrofoam. In data-oriented design, that same container arrives packed with 64 status flags. Every byte is useful. This means fewer trips to RAM, fewer cache misses, and a CPU that is never waiting for data. So I decided to be clever. I needed an array of booleans for the horde. The obvious choice was std vector of bool. Now, I knew exactly what vector of bool was. I knew it was a specialization that packs 8 booleans into a single byte. That was the whole point. I wanted that 87% memory saving. I thought I know what I'm doing, I got greedy and I merged the code. Fast forward 2 weeks, we spin up a parallel job system. Thread A handles zombie 0, thread B handles zombie 1. Logically, these are different objects, so this should be safe, right? Wrong. This is where my assumption failed. I knew the CPU read bytes, not bits, but I didn't connect the dots. Look at the assembly. For a normal byte vector, the CPU uses a single move instruction, atomic at the byte level. But for vector of bool, to change one bit, it has to read the whole byte, shift the bits, and write the whole byte back. This is the read modify write cycle. While thread A is modifying the byte locally, thread B reads the stale byte from memory. Thread A writes its work, then thread B writes its version, completely erasing thread A update. You just killed a zombie and the engine brought it back to life. I created a race condition not by sharing variables, but by sharing the byte they live in. This is why C++ veterans call this container a lie. If you ask for is alive at index 0, you don't get a boolean reference. You get a proxy object, a temporary helper class created just to handle that bit shifting logic. It breaks type safety, it breaks pointers, and as we just proved, it breaks concurrency. It even breaks the vector API. So how do we fix it? We stop being greedy. We replace vector of bool with vector of uint8. Yes, we're technically wasting 7 bits for every zombie. We're using 8x more RAM, but in exchange, every zombie gets its own unique memory address. Thread A gets byte 0, thread B gets byte 1. No overlap, no racing. But here is the ultimate irony. After fixing the crash, I got curious. Was the risk at least worth it for the speed? Look at the benchmark. The optimized boolean vector isn't faster. It's almost 3 times slower. Why? Because the CPU loves bytes but hates bits. To write to a uint8, the CPU just blasts data into memory. Boom, done. But for vector of bool, the CPU has to stop and perform bit surgery for every single zombie. Read, mask, shift, write. So not only did I create a race condition that corrupted our data, I actually made the engine slower. I trade correctness for performance and I lost both. A final warning. Data-oriented design is powerful, but it's ugly. Don't rewrite your UI or inventory system like this. Keep that clean and object-oriented. Use this only for the hot path, the 1% of code that runs every frame. In high-performance C++, correctness always beats theoretical compression. If you learned something new about the hardware reality of C++, hit that like and subscribe button. I'm making deep dives like this every 1 or 2 weeks. See you in the next one.